Hi everyone. Okay, so we have been working our way towards figuring out what a derivative is and how to calculate it. So hopefully you've picked up on the fact that a derivative is some sort of instantaneous rate of change, which graphically means the slope of a tangent line. In the context of a distance time function, it would mean velocity. And we got so far in the last section as saying that we needed to set up this average rate of change function. Basically, we needed to use a difference quotient, and then we needed to try and figure out what happened to that difference quotient as our time interval got smaller and smaller and smaller, or our x interval if you're just thinking about graphs. So that smaller and smaller and smaller idea is actually not trivial. It's kind of a big deal. So we're going to sidetrack right now and not worry about the slope and instantaneous velocity part of this quite so much, and instead really worry about this idea of limits, of letting a variable approach a value but not actually reach that value. So this first page again is a preview activity. So it would be great if you would pause and just try and think through this, and then I'll try and kind of zip through so that you can just make sure that you are on the right track. But that'll get us all on the same page about what we're working on here. So I've given you this function g, and we're supposed to just look at the graph and try and answer all of these questions. So basically this is working up to how do you find a limit graphically, which is one of the easiest ways to think about limits. Okay, so first we're just supposed to find the values of the function at -2, -1, 0, 1, and 2. At -2, it looks like the value of the function is 0. At -1, the value of the function is 3. At 0, it's a tricky one. There's a hole here, but there is a point down here at y equals 1. So g of 0 is 1. At 1, we again bypass the hole, and it looks like the value of the function is 3. And then at 2, it looks like no filled in point, so the function is undefined at x equals 2. Okay, so now we want to take a little bit different look at this. So I can show you a couple of these, but mostly what's important here is to see the picture. So we're supposed to complete some statements. The first one is as x gets closer and closer, but not equal to -1, g of x gets as close as we want to blank. So we know that our x's are sneaking in closer and closer, and we want to look at both sides here to -1, and we want to know what g of x, we want to know what our y value is getting close to. So this is what my x is doing, but really what I want to be looking at is I am on this curve. So as my x's scrunch in towards -1, my y's are getting close to 3. So nothing too crazy going on there. We already said the value of the function is 3, so it kind of makes sense that the y values are getting close to 3. Much more interesting when there's some sort of discontinuity happening. So the next one is looking at x equals 0. So our x's are creeping in closer and closer to 0, but we're stuck on the curve. So really what's happening is as our x's sneak in closer and closer to 0, our y's are getting closer and closer to the top here. Even though that's a hole, we're talking about what happens nearby. So our y's are getting closer and closer to 4. That one's a lot more interesting because g of 0 is actually 1. We are not getting that when we look at x is close to 0. The last one on our list to look at here is what happens as x is getting really close to 2. So as we work our way in, x is closer and closer to 2. We're stuck on the curve. And this one, it looks like our y's are going to get closer and closer to 1. Okay. And that one again is pretty interesting because g of 2 was undefined. So if I just ask you when x is 2, what is y, you can't answer me. But if I ask you when x is really, really close to 2, what is y really, really close to, you can answer me. So basically, this is the idea that we want to build up for limits. Limits are really boring when your function is continuous, but they can get really interesting near discontinuities. So the last part of this, again, I need to look at the graph, so sorry you can't see it. But the last part of it wants us to look at what happens as x is getting closer and closer, but not equaling 1. So here we have our x's. We want to think about them getting closer and closer into 1 on both sides. But we're stuck on the curve. So if we come from the right side, we're working our way up to the open circle. So our y is getting really close to 2. However, if we come from the left side, our y's are getting smaller and smaller, but they're hitting 3, not 2. So we're getting two different behaviors. And the question is very carefully worded. So let me move down to it. Keep that picture in mind. What happens? Oh, no, this is the part I want to look at. Does the function g of x get as close as we would like to a single value? So that's kind of the key. If I make my x close enough to 1, can I get my y values as close as I could ever hope to get them to one single value? That's the really key thing. And the answer here is no. On the right-hand side, we're getting really close to 2. And on the left-hand side, we're getting really close to 3. And no matter how close my x is to 1, I can't guarantee that if I go a tiny bit each direction, my y's will be really close to 1 value. They'll always be at least 1 apart. So that is a big problem for limits. That's the one thing. Sorry, you couldn't see my squiggling there, could you? So no matter what, we'll have this space in between our y values if we looked at the left and the right side. And that's a no-go for limits. Okay, thanks for watching.